GCE Advanced Level Chemistry Practical Series, experiment number 26, examination of properties of phenol. In this practical, we are going to observe the acidic nature of phenols and what chemical reactions that revolve around phenols. Keep in mind, when handling phenol, you have to be very careful. It is toxic, and when you are handling phenols, always wear gloves and make sure that it does not come into contact with your skin. Now, let's move on to our reagents. For this practical, we will be using these chemical reagents and these equipment. We have here phenol, we have bromine water, we have sodium carbonate, sodium hydroxide, ferric chloride, and dilute ammonia. Apart from those chemical reagents, we will be using droppers, test tubes, 2 beakers, and we have our red litmus, our blue litmus, and pH paper. We will be using a filter paper, a funnel, and a retort stand. Now, let's move on to our first part of this experiment. Let's start with the first part of our practical. We are going to observe the solubility of phenol in water, and then we will be testing the pH value of a phenol solution. We will be taking a test tube, and let's take a small amount of phenol into our test tube. This is enough. Now, you will observe the color of the phenol that we have in this test tube is between a pink and a red color. This color is there because the phenol that we have in this test tube is not 100% pure. A 100% pure sample of phenol will appear to be colorless, but if there are any impurities present, the color you will be observing is this, a pink-red color. Now, let's add a small amount of water to this and see whether this phenol sample dissolves in water. We will be using a wash bottle for that, and we will be adding a small amount of water very carefully. At first glance, you would see a layer separation. You can see the phenol layer at the bottom and the water layer at the top. The phenol layer will sink to the bottom as phenol has a higher density than water. So therefore, you will observe the phenol layer at the bottom and the water layer at the top. However, phenol is known to be moderately soluble in water. 8.3 grams of phenol can dissolve in 100 milliliters of water. So this is a moderately soluble organic substance, which means some amount of this phenol will dissolve if I shake this test tube. As you can see, upon shaking the test tube, most of the phenol did dissolve in water. However, there is still a small portion of phenol that is not dissolved in water. So this indicates that phenol is moderately soluble in water, and it dissolves in water to form a phenol solution. Now, this is due to the presence of OH group connected to the benzene group. This allows phenol to be moderately soluble in water. Now, let's check the pH of this mixture. In this part of the experiment, we are going to see the acidity or the basicity of our phenol solution. In order to do that, we will be using a red litmus paper and a blue litmus paper. Later on, we will be using a pH paper to determine the pH value of this phenol solution. Red litmus paper will turn blue in the presence of a base. Blue litmus paper will turn red in the presence of an acid. And we have here a control. So this blue litmus paper is there to give you an idea what the color change would be when it is added with water. Keep in mind, water is neutral, so therefore the pH paper should not change its color, but it will give you an idea when water is added, when the pH paper gets wet, what the color you observe will be. So without further ado, let's add a small amount of the phenol solution into our red litmus paper and to our blue litmus paper. And then let's add a little bit of water into our control. As you can see, the color of the red litmus paper did not change. It remained red. However, the color of the blue litmus paper changed slightly to a red color. So to see this color change very clearly, we can compare the blue litmus paper that was made wet with distilled water. You can see normally when the blue litmus paper is made wet, it is going to be remaining blue, but you can see the blue litmus paper added with the phenol solution has turned red. So very clearly we can see now the color change that has taken place in our blue litmus paper, because we can compare it against the control where we added a little bit of water to a piece of blue litmus paper. Now, you would not see a very dark red color in the blue litmus paper, as phenol is not a strong acid. It is not going to be indicating strong acidic properties. So that is why the color change you see in the blue litmus paper is not very prominent. Now, let's move on to our pH paper. We have our pH paper book here, and we will take a pH paper out of that book, and let's add a small amount of phenol solution into our pH paper. As you can see, when you added small amount of phenol solution into our pH paper, the color that the pH paper turns to is somewhere between yellow and red. It is an orange color between yellow that you observe here and red here, which means the pH of this solution, phenol solution, is somewhere between pH 3 and pH 5. This is not red and this is not yellow. It is between red and yellow, which means the pH of the phenol solution we have is between pH 3 and pH 5. Now, let's move on to the summary. We observed that phenol was moderately soluble in water. 8.3 grams of phenol can dissolve in 100 milliliters of water. And apart from that, we noticed the phenol solution that we made is slightly acidic. We observed this with the use of litmus paper. We saw the red litmus paper did not change into a blue color, indicating that this in fact is acidic, and the blue litmus paper turned into a red color, confirming that the phenol solution we have here is acidic. Then we moved on to adding the phenol solution onto a pH paper, and the pH paper turned to an orange color, a color between red and yellow. This indicated the pH of the phenol solution is somewhere between pH 3 and pH 5. Now, let's move on to the next part in this experiment. In this part of our experiment, we are going to see how bromine or bromine water reacts with phenol. Now, to test this, we will take a test tube and take a small amount of phenol into this test tube. We will use this test tube to add a small amount of phenol into our bromine water because I want to compare the colors of the two solutions you will have. Now, we have our bromine water solution. Now, if you take liquid bromine, it will appear brown or red-brown in color. Now, this is appearing a yellow color because we have bromine water here. If you take liquid bromine, the color of liquid bromine will be red-brown. What we have here is bromine water, and you can see a yellow color in this bromine water sample we have here. The color of this bromine water is due to the presence of Br2 in this sample. Now, let's add a small amount of phenol into our bromine water. Observe the color of phenol. Due to the impurities present in this phenol sample, we can see it is pink or pinkish red in color. Now, let's add this phenol into our bromine water. As you can see, upon addition of phenol into bromine, you can see the color of bromine water disappeared. At the same time, I hope you can see the formation of a white color precipitate or white color powdery substance inside this reaction mixture. What happens here is when phenol is added to bromine water, the bromine reacts with phenol to form tribromophenol, which is insoluble in water, which is a white color precipitate. So, the color of the bromine water disappeared and it formed a white color precipitate that is suspended in the aqueous medium here. Now, let's add a little bit more bromine water to see whether we can see a change in color or whether we can see a bit more precipitate forming here. As you can see, when I add more and more bromine, the precipitate that is formed increases. The precipitate that you see here is 2,4,6 tribromophenol. 2,4,6 tribromophenol. Now, for comparison, let's take a small amount of bromine water and compare the two colors. Bromine water was yellow in color, and now you can see after adding phenol to this bromine water, we saw the color of bromine water disappeared, as well as a white color precipitate started to form, which is 2,4,6 tribromophenol. We'll add this sample of bromine also into this mixture. You can see even addition of that portion of bromine water did not change the color of the mixture over here. It remained colorless, and at the bottom what you can see is the portion of phenol that is insoluble in water. And in this section of the test tube, you can see the bromine water that was present completely decolorized and formed a white color precipitate which is insoluble in water due to reaction with bromine and phenol. In that test, what took place was when bromine came into contact with phenol, as phenol is quite reactive, it reacted well with bromine and formed 2,4,6 tribromophenol, which is insoluble in water, and due to this reaction the color of bromine water got decolorized, and due to the product being insoluble in water, we saw the formation of a white color precipitate. You can see the precipitate sinking down to the bottom. In this part of our practical, we are going to see how phenol reacts with sodium carbonate. We need to observe if phenol is acidic enough to have a reaction with sodium carbonate. Now, we will be taking sodium carbonate solution for this. Let's take a test tube and add a small amount of sodium carbonate into our test tube. We have our sodium carbonate solution here. Let's take our phenol and add a small amount of phenol into this sodium carbonate. As you can see, upon addition of phenol into our sodium carbonate solution, they did not mix. There is a clear layer separation, and if you mix it a little bit, you will see some amount of phenol will dissolve in the aqueous medium like we have observed before, but we do not see evolution of a gas. When sodium carbonate is reacted with an acid, we see the formation of carbon dioxide gas. Carbonate anion will react with the H pluses and will form carbon dioxide and water. In this reaction, we saw when you mixed phenol with sodium carbonate, and when we mixed it well, we did not see any gas evolving from this mixture. indicating that phenol did not react with the carbonate anion. So therefore, we do not see formation of carbon dioxide gas. We did not observe any bubble formation or effervescence in this mixture. And the color of the phenol still persists, indicating phenol did not become phenoxide ion, because when phenol releases the H plus ions attached to the OH group, it forms phenoxide ion. This will allow the phenol to dissolve in water. You can see the layer separation is still very clear, indicating it did not react with sodium carbonate. This tells us phenol is not acidic enough to show a reaction between sodium carbonate or sodium bicarbonate. Now, let's move on to our next test. In this part of our test, we are going to see the reaction between phenol and sodium hydroxide. First, let's take a small amount of phenol into our test tube. We have our phenol here. And to our phenol sample here, let's add a little bit of water. We will add a small amount of distilled water with the help of a wash bottle. You can see before mixing, you can see a little bit of layer separation here. We saw phenol is moderately soluble in water, but if I don't mix it, you will see the two layers separated like so. Now, to this phenol solution, let's add a small amount of sodium hydroxide and see what the observations are. Note what happens when sodium hydroxide is added to this mixture. As you can see, when sodium hydroxide is added, and if you shake it, the phenol that did not really dissolve in water earlier starts to mix well with sodium hydroxide. But now, after sodium hydroxide is added, you can see it entirely dissolved in the presence of sodium hydroxide and formed a clear solution. When you added just water, we saw a layer separation, but when we added sodium hydroxide and mixed it, we saw the layer separation ceases to exist and the phenol dissolves well in sodium hydroxide. The reason for this is the reaction that takes place between phenol and sodium hydroxide. Phenol is slightly acidic, so in the presence of sodium hydroxide, phenol reacts with sodium hydroxide and forms sodium phenoxide. The OH minus ions from sodium hydroxide reacts with the H plus that is released from phenol, and phenol produces phenoxide ions, and together with the sodium plus ions in the medium, they will form sodium phenoxide. Therefore, the phenoxide ion is soluble in water. You can see there's no layer separation, as well as you can see a clear solution has been formed when we react sodium hydroxide with water. Now, let us do the same test, but before we add sodium hydroxide, let us add a small amount of phenol and add a small amount of water, and let us mix it really well. We can see some amount of phenol dissolves in water and creates this cloudy solution. And to this phenol solution, let us add sodium hydroxide. As you can see, when sodium hydroxide is added little by little, the cloudy nature of the phenol solution disappears and it forms a clear solution. Now, if you mix it really well, you can see the phenol completely dissolves in sodium hydroxide and forms a clear solution. This is again because of formation of phenoxide anion. Although phenol is moderately soluble in water, phenoxide anion is soluble in water. Therefore, you will see the formation of a clear solution that has a slight pink hue to it. However, we will see the formation of a clear solution when sodium hydroxide is reacted with phenol. Now, let us move on to the next part of our experiment. In this part of our practical, we are going to observe how ferric chloride reacts with phenol. This is an acidic salt. Therefore, we need to react the ferric chloride solution with dilute ammonia and produce a neutral ferric chloride solution. First, let us observe the pH of ferric chloride solution. We will take our ferric chloride solution and we will test it with the use of a pH paper. We will take our pH paper to this pH paper, we will add a drop of ferric chloride. Let us see what happens when a drop of ferric chloride is added to our pH paper. As you can see, the color of the pH paper turned a red color. Let us compare this color against the pH guide provided with a pH paper booklet. Now, let us observe what color we see here in this pH paper. It is certainly not pH 1. It does not align well with pH 2 as well. It is very close to pH 3, and if you compare it against pH 4, you will see not very close to pH 4. So, this must be having a pH of around pH 3. It does not perfectly align with the color. However, this color indicates it is very close to pH 3. That means the ferric chloride solution we have here has a pH of around pH 3. Now, let us move on to preparing a neutral ferric chloride solution. For that, we will be using a beaker. Let's use our ferric chloride solution. We'll transfer the ferric chloride solution into a beaker. As you can see, you can observe the color, the brown or orange brown color very clearly. Now, to this, we will be adding dilute ammonium hydroxide or dilute ammonia. We will add dilute ammonia drop by drop until we observe a brown color precipitate. When you add ammonium hydroxide, you can see before mixing it the formation of a brown color precipitate. But if you mix it, you might see it disappearing. We'll add a few more drops of ammonium hydroxide. If you observe a persistent brown color precipitate forming, that indicates the presence of ferric hydroxide. We still can't see a persistent precipitate here, meaning we should add more ammonium hydroxide. So what happens here is, since the medium is acidic, when you are adding ammonium hydroxide, the hydroxide ions reacts with the acid H plus ions, or hydroxide ions react with the H plus ions and remove the H plus ions from the aqueous medium. And thereby, we make the ferric chloride solution neutral. But after all of the H plus ions are removed from the medium, the additional ammonium hydroxide that is added to the medium will give us a ferric hydroxide precipitate, a brown color ferric hydroxide precipitate. This indicates that we should stop adding ammonium hydroxide and start filtering the solution to obtain the neutral ferric chloride solution. We still cannot see a precipitate, so let's add a few more drops. Now you can see the formation of ferric hydroxide precipitate. Very fine precipitate is formed here. I'm not sure whether the camera can capture it. However, a fine ferric chloride precipitate is formed here. Before we move on to filtering the solution, we can double check if we have formed a neutral solution by using a pH paper. We have our pH paper here. Let's add a drop of neutral ferric chloride here to see if the solution has actually become neutral. As you can see, when we are adding dilute ammonia into this, the color of the solution starts to change, and you can see a brown color precipitate has started to form. You can see it coating the walls when I mix it, indicating that we have our brown color precipitate ferric hydroxide. So now let's filter the precipitate out from this suspension, and we'll obtain the supernatant of this suspension. The supernatant is going to be neutral ferric chloride solution. So, in order to filter this precipitate out from this suspension, we will be using a filter paper such as this, and we will be using this setup. So, we have our funnel set up here connected to a retort stand holding up the funnel, which will be allowing the filtrate to be filtered out into a beaker. Now, when you are using a filter paper, you have to make sure that you use it the right way. We have to fold it once in half like this. Then you can fold it again in half, and you will be folding it once more. You can fold it one more time. Now, after you have folded it like this, you will be unfolding it, and you will arrange it in a manner like this. You have to make sure that you keep folding it in the right manner, that you like you see over here, so that you can create an open structure that will allow the suspension to be filtered properly. So, once you have done that, you can open it up like this. Now, this will increase the surface area that is going to be used for the filtering process. So, when you have a filter paper folded up like this will increase the surface area that is used for filtering of this suspension. So, now I will place this filter paper on top of our funnel, and now after placing our filter paper on the funnel, we can wet the filter paper with a little bit of distilled water. This will fix the filter paper in place and will allow the filtering process to be a little bit more efficient. So, after wetting our filter paper, we will start transferring our suspension onto our filter paper. We will make sure the suspension is mixed really well, and then we will transfer it onto our filter paper. As you can see, when we transfer some of our suspension onto this filtering mechanism, you can see the solution is separated from the precipitate. On the filter paper, you will see ferric hydroxide precipitate remaining, and filter paper will filter out the ferric chloride neutral solution. So, what you have here in the beaker is our ferric chloride neutral solution. Let us filter out the ferric chloride neutral solution completely, and I will show you the brown color precipitate that we have on our filter paper. That brown color precipitate that you will be seeing on the filter paper is ferric hydroxide. You can see the filter paper is now coated with a brown color precipitate that is our ferric hydroxide. and in our beaker is a supernatant or the filtrate that is going to be our ferric chloride neutral solution. Now we have allowed the filtration to happen for a while now, and you can see, if you take a look at the top view, we can see the brown color precipitate remaining on the filter paper. What you see here is ferric hydroxide precipitate, which is a brown color precipitate, and you can see at the bottom the filtrate is a yellow orange color. This is due to the presence of Fe3 plus ions. We have our neutral ferric chloride solution here. Neutral ferric chloride solution is present here. The precipitate is present in the filter paper. The ferric hydroxide precipitate is present on the filter paper, and the filtrate will contain our neutral ferric chloride solution. Now let's add phenol to this ferric chloride solution and see what we would observe. We will take a test tube, and to this test tube I will be taking a small amount of ferric chloride solution. This is our neutral ferric chloride solution. Now we have our neutral ferric chloride solution here. Now to this, let's add a small amount of phenol. Let's add a drop of phenol. As you can see, when we add a small amount of phenol, the color of this solution is starting to change. I have not yet shaken it, but you can see a violet color forming when we add phenol to our ferric chloride solution. Let's mix it to see the color very clearly. As you can see, a violet color solution was formed. Normally you saw phenol was not dissolving very well with water, but you can see here all of the phenol that we added dissolved really well and produced a violet color solution. Now this violet color solution was formed due to phenol reacting with ferric chloride solution and forming phenoxide anions. The phenoxide anion and Fe3 plus ions form a complex that is purple in color, or that is violet in color. That is why you observe a violet color when you react neutral ferric chloride with phenol. So we can use this test to identify phenol. If you react neutral ferric chloride with phenol, you will see the formation of a complex between Fe3 plus ions and phenoxide anions, which is violet in color. This could be used as an identification test for phenol. And now we are going to add a small amount of hydrochloric acid to observe what happens when we acidify this medium. We will take our hydrochloric acid. We have here our hydrochloric acid. To this, to our purple color solution we have here, let's add a small amount of hydrochloric acid. Observe what happens when hydrochloric acid is added. What happens to the color? What is your observation? The color of the solution is starting to disappear. And we are noticing the color that we had earlier. Initially, when we were starting this experiment, we saw the ferric chloride neutral solution we took to our test tube had the same color, but when we reacted it with phenol, we saw the color turn to a purple or a violet color. But upon addition of HCl, this violet color disappeared and reformed the yellow color that we observed in the initial stages. This is because upon addition of H+, phenoxide anion converts back into phenol. Therefore, you break the complex that is formed between Fe3+ and phenoxide anion, because phenoxide anion will no longer be there. Instead, it will form phenol. So therefore, due to the absence of Fe3+ and phenoxide anion complex, we do not observe the violet color. Instead, we have the yellow color that we observed in the previous Fe3+ neutral solution. In summary, in this part of our experiment, we initially started with observing the properties of ferric chloride salt. We observed that the ferric chloride salt is an acidic salt. After checking the pH of ferric chloride solution that we have, we decided we need to obtain a neutral ferric chloride solution. And we prepared a neutral ferric chloride solution by adding ammonium hydroxide or dilute ammonia until we obtain a brown color precipitate. Afterwards, we filtered the suspension and we obtained our brown color precipitate ferric hydroxide on the filter paper, and as the filtrate we obtained our ferric chloride neutral solution. We have our ferric chloride neutral solution as our filtrate. Afterwards, we took a small portion of ferric chloride neutral solution and reacted it with phenol. When we reacted it with phenol, we observe when ferric chloride neutral solution reacts with phenol, it produces a violet color solution. This is due to Fe3+ ions forming a complex with phenoxide anions. Upon addition of hydrochloric acid to the purple color solution we had, we were able to decolorize the purple color and obtain the color of ferric chloride that we observed earlier. This is because when H+ is added to the medium, phenoxide ion reacts with the H+ and forms phenol again. Therefore, the complex ion that gave us the violet color solution will break, and therefore we will not observe that violet color. So the purple color or the violet color solution was due to a complex formation between Fe3 plus and phenoxide anion, and when H plus is introduced, phenoxide anion will turn into phenol, thereby breaking the complex. This is all for the final part of our experiment. Now let's move on to important theory parts and questions revolving around this practical.